open up 5.1 and 2 notes. So those should be in there for you. So you can follow along from what I pop up here, or you can access those on your own. Okay, so am I showing those notes on my screen? All right, great. All right, I appreciate that. So what we're looking at here is a lot of stuff that you already know. Okay, so you've already seen these identities that we've studied before, but it's a good refresher to sort of get them down. So we have these basic identities where we take the reciprocal of functions. So we said, hey, if you know sine, cosine, and tangent, it's easy to find cosecant, secant, and cotangent of an angle because you just take the reciprocal of those three. We had ratio identities where we could get tangent by just knowing sine and cosine. So cotangent is sine over cosine and cotangent is cosine over sine. We called those the ratio identities. And then probably the most important identity is the Pythagorean identity. So we found out from the unit circle specifically that the cosine of theta squared plus the sine of theta squared is equal to 1. So if I have any point on the unit circle, remember the x and y components are going to be cosine and sine, right? The x is cosine and the y is sine. So if I look at that triangle, if it's on the unit circle, my radius is length 1. So I have x squared plus y squared is equal to 1, but x is cosine and y is sine. So that's one of the most important identities there, that Pythagorean identity. Of course, I can solve for sine squared and cosine squared. And then if I want to solve for sine and cosine, we do have to consider the plus and minus square roots because sine squared, it's not a function. So if we're trying to use that to solve for sine, we'll get 2 roots of that. There's alternate Pythagorean identities. So if I divided the Pythagorean identity by cosine squared, I would get that first one. 1 plus tangent squared is equal to secant squared. If I divided the Pythagorean identity by sine squared, I would get the second one. So cosine squared over sine squared is cotangent plus 1 is equal to cosecant squared. Okay. So we've learned all those. And what we're going to do is we're going to talk about proving identities here. So we've talked about the fact that it's easy to, in trigonometry, have different ways to express things, right? So I have to be careful when I grade. You have to be careful when you show work because somebody can get one thing. Ali could get one answer and Michaela could get another one. They could look a lot different, but they could be exactly the same. They could be equivalent. And so what we're going to try to do is prove identities. So the first thing we want to sort of look at is strategies. So these are helpful strategies. They don't always work, but they're definitely important to keep in mind. So proving identities, as we've sort of seen, if you know the identities to work with, most of the time they're fairly straightforward. However, there are some that can be really nasty to prove. The thing that we have to keep in mind is that when we're proving something, we can't assume that it's true. We hope that it's true, but we want to take one side and construct the other side. So we really don't assume it's true. We're trying to prove that. And I'm going to try to be a good role model. And whenever I prove something, I'm going to try to construct it that way. However, a lot of them aren't that straightforward. So it is possible to work on one side at a time and try to get them to meet in the middle. So here are our strategies. Usually it's best to work on the more complicated side first. So if you have like more than one term, that's probably a better side to start with. But it sort of depends there. Look for trig substitutions involving the basic identities that may help simplify things. So those are sort of holistic things to look at. So if you see these identities, if you want to simplify something more complicated, like 2 terms down into 1, you're probably going to have to combine those together somehow. So look for those identities that can help. Look for algebraic operations. And we sort of talked about this back in chapter 1, I think, such as adding fractions, distributing, factoring that may simplify the side that you're working on. So we oftentimes want to find a least common denominator to put two things together. We want to factor things to cancel things out. So we can not only use algebra, but we have those identities to use too. So this becomes multi-dimensional there. If you can't think of anything else to do, try to change things into sines and cosines. See if that helps. Okay, that amazingly does work sometimes, where you're just like, man, I don't know what to do. Let's just turn everything in cosines sines and see what we're doing there. And always, this one's important, always keep an eye on the side you're not working with to make sure you're working toward it. So there's been times actually in this class in past semesters where I sort of went off on a different way, and I looked down and then I looked up and then I was like, oh, wow, this is nothing like the other side. I was like, okay, hold up, let's go back a few steps and go a different route. So it's always important to keep your eyes on the prize to make sure that you're actually working towards what you want to solve. So those are some good strategies to think about when we're proving things. All right. So let's just try to fill some of these in for strategies. So sometimes it's really just sort of important to get these strategies down. So an identity is a statement that two expressions are, what do you think? Blank for all replacement variables for which the expression is blank. So if it's an identity, those have to be equal, right? At least where that expression is defined. Whoops. Okay. To prove or verify an identity, we usually start with the blank side of the equation. Well, I would say more difficult side. But you could say left side of the equation and simplify it until you it's identical to, I guess they were looking for the right side maybe, but I'm just going to say other sides because that's what my strategies told me to do. Okay. To prove an identity, it's usually best to start with the more, okay, there is where they're getting at it, more complicated side, right? Side first. If nothing else comes to mind, try changing everything into what and what?
Sine and cosine.
There you go. Thanks for your help. So into sines and cosines, excellent. And then simplify. To investigate if an equation is an identity, graph the left-hand side. So we haven't talked about this. So you can graph one side and the other side comparatively or separately and see if the two graphs are equal, are the same. So see if they look the same. And so we will be looking at some graphing here throughout this section too, just to make sure we have that tool. So we might as well check things out if they're equal. To prove that an equation is not an identity, find a value of the variable for which each expression is false. So sometimes, you know, you can have something that looks like an identity, and it can be true for almost all the variables, but there might be a few that are not. If there's one counterexample, then it's going to be false. So find a value of the variable for which each expression is, whoops, I should have said this wrong. Let me undo that one. For which each expression is true, but it makes the statement false. And this value is called a counterexample. So if you, if mathematics is your thing, if you enjoy mathematics, you might get into proving things. And proving things, I mean, even at JCCC, we have some classes where we prove things. when you're proving things, sometimes it's easier to show something's false. It's easier to show something's false usually than true. You just have to find one counterexample and that will do it. Okay, so these are some good strategies and terminology. So let's go ahead and advance here. And I like to start out with a little algebra. So let's look at some factor practice here. So I want to try 10 and 11. So if I have something like x to the fourth minus y to the fourth, is there any way that you can think of simplifying this, something like that? So we're looking at number 10.
Are we looking at 7a, the x squared minus y?
We're looking at, sorry, we're looking at number 10.
Oh, okay.
Yeah. So Ali?
I think we can put x fourth equals x prime squared.
Okay.
And y fourth equals y prime squared.
Okay.
And then we will have x prime square x prime plus
Okay.
y prime squared
Okay.
multiply by x prime square x prime plus minus y prime.
Okay, great. So this is just the difference of squares, right? So your x prime and y prime, we could say that those were x squared and y squared, right?
Mm-hmm.
But I like the way that you did this. So, you know, if you're a little bit unsure about using the x squareds and y squareds, you can start with primes. So this is just the difference of squares there. Great, that's right. And so let me see if I can expand this just a little bit. There we go, there we go, that's better. So is there any way I can simplify this even further? What do you think, class?
We know that x squared plus y squared equals to 1. For y and cosine and sine, no?
Okay, so if it was trig functions, that would be something, that would be an extra dimension we have. That's right, that's great. But this is just algebra. So what can we do now? Is there something else we can sort of simplify there? What about the x squared minus y squared?
Yeah, it's the same.
It's the same, right? It's the difference of squares again. Yeah, great. So excellent. So what we can do here, nice. Oh, I pinned myself. I don't like that. Remove pin. All right. So what we can do here is we can use difference of squares, and we can use it again. So I can't factor down sum of squares anymore under the real numbers, but this x squared minus y squared, I can do x plus y and x minus y, right?
Mm-hmm.
So that's how I could factor out the difference of fourths. Well, we can do the same thing for b with sine and cosine. So I could do the same exact thing. This is just going to be sine squared theta. Nice job, Ali. Thank you. Plus cosine squared theta times sine squared theta minus cosine squared theta. And Ali was saying by the Pythagorean theorem, if we had, or identity, if we had cosine squared plus sine squared, that's 1, right? So I can use that Pythagorean identity to make this 1 times sine squared minus cosine squared. And of course, I need those angles in there. So never forget your angles, please. Try not to do that, because cosine and sine just by themselves don't really mean much. And then if I wanted to, I could use difference of squares again, right? So I'd have sine minus cosine times sine plus cosine. Okay. So notice a lot of things we're going to be doing here. We can do the same thing with algebra, and then we can use other identities, trig identities, to even simplify things down more with our trig identities. Great, great. Questions there? All right, let's take a look at one more technique that we use. So this is a factoring technique that we're using there. So I want to look at 11 down here now. And sometimes if you have a complicated expression in the denominator, like 1 plus a square root or 1 minus a square root, we can simplify that radical out of the denominator by multiplying by the conjugate. Do we remember what the conjugate is of a number? What do you think, Benjamin? Or do you remember? It's okay if you don't.
I can't. I forgot it.
No worries, no worries. Jonathan, do you remember a conjugate of a number?
Yes.
Yeah. Okay, that's all right. So go ahead, Ollie.
I think this is going to be 1 minus root 3 divided by 1 plus 3 equals 4. So
Okay.
1 minus root 3 divided by 4.
Exactly. So nice job. Sometimes when we have a complicated expression in the denominator, we want to simplify that and get that radical up in the numerator. So what we do is we multiply by the conjugate, and the conjugate of a number is just going to be that same expression here, but you're going to have the opposite sign in between them. So I'm going to multiply by 1 minus root 3, but I can't just multiply by 1 minus root 3 in the denominator. I have to do it in the numerator too. So there's a ratio of 1. The reason why this gets that root 3 out of the denominator is because we're using the difference of squares in reverse now. So if you sort of look back up to what we did here, for instance, going from x squared minus y squared to x plus y, x minus y, we're going this way this time. So I have x plus y times x minus y in that denominator. That's 1 plus root 3 times 1 minus root 3. So what that should simplify to is 1 squared minus root 3 squared by the difference of squares there. But we can distribute things out. So I have 1 times 1, that's 1 squared. I have the,
minus 3.
Minus root 3, that's right. I have plus root 3, so those things subtract out, right? And then I have root 3 times root 3, negative root 3, so I have negative that root 3 squared, right? All right. So when I take that out of the denominator, and if you don't care, I'm just going to write right over 12. I have 1 minus 3, which is a negative
minus
2.
2.
Yeah. And then in the numerator, I have 1 minus a root 3. So 1 minus a root 3 times 1, still 1 minus a root 3. And we really don't want to leave that negative in the denominator. So
root 3
what I can do
minus 1 divided by 2.
Make it root 3. Yeah, so I can take that negative out, distribute it in the numerator. So that would be a negative 1 plus root 3 over 2. So I sort of take this negative out or distribute it through to both there. So what's happened here is I've got that radical out of the denominator. It has to go somewhere, so it does come up to the numerator, but I've somehow simplified that so I have just the radical in the numerator. So we're going to use the same technique when we see trig functions that are added in the denominator. So if I want to do part B, I'm just going to multiply by 1 minus cosine x and 1 minus cosine x here. And you can sort of see why I might do this in a minute. So I should get 1 times 1 minus cosine plus cosine. So those subtract out. And then I have minus cosine squared. So I have 1 minus cosine x in the numerator and 1 minus cosine squared in the denominator. So the reason that we do this with trig functions, do you see that identity that works in the denominator? Yep. Okay, what is it, Emily?
It would turn into sine squared or sine.
Exactly.
Yeah.
It's going to turn into sine squared. Yep, you got it. Nice job. So that's the Pythagorean identity, right? Is that what you were going to say, Benjamin? Excellent. All right. Nice job. So we can use that to sort of help us use that Pythagorean identity. Sorry that there's so much stuff going on there. But that's the idea of the conjugate. So those are two big algebraic techniques that we're going to use in conjunction with the identities to sort of factor out trig functions and then multiplying by the conjugate to sort of reduce those. Questions? All right, so I think that we've built this up enough. So let's look at solving some of these. Okay, I'm going to clear this out. Oops. All right. So I'm going to look at this one here. So prove the following are true. Listing the identities that you use. So I want to show that cosine of the fourth of t minus sine of the fourth of t over sine squared t is equal to cosine squared t minus 1. So if we use our techniques, we usually start on the more complicated side. Which would you say is the more complicated side here, Katie?
I would say the one with, you know, cosine over sine squared. You got a lot more going on that side than on the other side.
Oh, I totally agree with you. Yeah, we got a lot more going on that left-hand side. Great. Yeah, so I think I would start with that. Nice job, Katie. So let's go ahead and start out with that left-hand side. So when I prove this, and sometimes, you know, I'm going to just have to start and then sort of go off to the side. Sometimes it doesn't work out just exactly how you'd want it to. So you have to try again. But I'm going to start out with that left-hand side. So this time I'm going to start out with the left-hand side. I want to write that down. And then I'm going to ... go over and prove that that's equal to cosine cotangent squared minus 1. All right. So I think we've seen a technique we can use already, right? Gavin, do you see something that we can use to simplify that numerator?
Differences of squares on top.
Yeah, exactly. So we sort of got set up for this one. Nice job, Gavin. So we can use that difference of squares. Cosine squared squared minus sine squared squared is cosine squared minus sine squared times cosine squared plus sine squared. So you want to show this step, but you don't have to have any justification there. Because you're showing the factoring technique. Okay. So notice that the left-hand side, we do have sort of two terms here. And the right-hand side, we have one term here. And the right-hand side, we're trying to break that up to 2. So at some point, we'll probably want to try to break that up. But let's just go with what we have for now. Okay. So now, are there any identities, trigonometric identities we can use on the numerator, Michaela?
The cosine squared t plus sine squared t would equal 1.
Exactly. Great. So we can use that Pythagorean identity to turn that second factor into 1. So I'm going to say cosine squared t, great job, Michaela, minus sine squared t times 1 over sine squared t by that Pythagorean identity. So you see I am sort of messily putting what I use here. So that shows the reader exactly what I'm doing. Okay, so now that we have that simplified, it might be time to take a look, to just sort of come back out and take a look and see, I have to split that first term into two terms. So is there any way now that I could split that into two terms? What do you think, Tomas?
Would it be cosine minus sine t over sine?
Let's see. Not quite, but notice we want two terms, so we want to split it into two terms there, and we only have one here. But you know what? If I had something like 1 plus square root of 2 over 5, couldn't I split that up into 1 over 5 and plus square root of 2 over 5? So maybe I could use that sort of thing to split this up over the same denominator. So what do you think about that? How can we split that up over the same denominator? You need some help?
Yeah, I'm not sure. Yeah.
Okay, no worries. Okay, go ahead, Benjamin.
So we'd split into two individual fractions, cosine to the power 2 t over sine to the power 2 of t, and sine to the power 2 of t and oval sine to the power 2 of t. So that'd be 1 on that white term, and that'd be cotangent square root 2, obviously, since on the left side.
Excellent. Very nice. So, okay. So I want you to see a couple things here. So I came back out and I sort of look at it. I was in the trees, and then I came back out of the forest and looked back down to where I'd been, and I was trying to see how to get out. Okay, that's like some weird metaphor for what we're doing here. But I could have got lost here, because I could have easily done what we did with that first part and used cosine t minus sine t plus times cosine t plus sine t, right? I could have factored that out, and that looks better algebraically. However, that's not going to get me what I want on the right-hand side. So at that point, I had to make a decision. And since I had two factors on the right-hand side, two terms on the right-hand side, and I have one denominator on the left-hand side, I thought I needed to split those out. And then Benjamin helped me put those together. Good. So even though something seems obvious to do, I would do this in algebra, sometimes it's going to lead you down a wrong path for trigonometry. Nice. Okay. So, and also be careful. If you have like a sum in the denominator, you can't split those apart. So good being cautious. It's always good to be cautious with splitting up two terms. If I had like sine squared plus 1, I couldn't put cosine squared over sine squared and cosine squared over 1. That doesn't work. But when I have one singular denominator, I can do that. So there's an algebraic step. And then as Benjamin was saying, cosine over sine, that's going to be cotangent squared by a ratio identity. And then another algebraic identity there. Of course, when we take something and divide by it, we get 1. So we could say that that's true, and that gives us the right-hand side. And finally, we would say by the ratio identity. So we use one other trigonometric identity there. Okay. Very good. So notice what I did. I tried to model very good behavior for you. I started with one hand side. I didn't assume that they were true at any point. I started with one side, tried to get to the other. and I use logical steps of algebra and trig to get to that other side. At some point, I might have had to say, hey, I'm not really sure what cotangent squared is, so I might have gone over there and said, okay, cotangent is cosine over sine. So I might have just put this over here so I could keep my eyes on the prize. And then maybe, oh, I could say, oh, at this point, yeah, I see a cosine squared over sine squared, and then a sine squared over sine squared, which will give me 1. So those are things that you can sort of see by simplifying that left-hand side out just a little bit, or right-hand side, I should say. But just remember not to work on those at the same time. Okay, questions? All right, I'm gonna try, and I don't know if it'll let me do this. So maybe I'll stop share for a minute. I'm gonna try to go into Desmos here. Okay, so let me just go ahead and show you. Right, I'm gonna try to share my canvas. Okay, hopefully this all will work. So I think I'm sharing my canvas now. I'm actually just sharing the same thing. Let me see. Come on, there we go. So am I sharing my canvas now? Yeah, great, thank you. So if I go into assignments, this project 3 is going to be the one that you want to do by next Tuesday. And this one should take you to the project, Trigonometric Identities. And so what I have here are basically steps that we want to line up to get these in the right order. Now, last night, I think I was playing around with this, so blah, blah, blah. Don't pay attention to what I'm doing. All right. Okay. So part of this exercise is going to be, I have the steps to solve the identity, and we just want to sort of justify those steps and put them in order to go from the top down to the bottom. So let's look at this one together. Can you all see my Desmos project there? Yeah, okay, great. Okay, so it tells us we're going to prove this identity, and it says, hey, start with cosine x times cosecant x plus tangent x. So I'm going to find that, and I'm going to drag it to the top. Okay. So if I'm trying to keep my eyes on the prize, I want cotangent x plus sine of x. What would you do algebraically, probably in your next step here to work your way down? What would our next step be?
Distribute.
To distribute, exactly. So we notice that the right-hand side has 2 terms. I have 1 term on the left-hand side, so I'm going to distribute that cosine through to cosecant and tangent. Okay, great. So what's another technique we can use at this point to sort of get things on the right track?
I think we use ratio identities next.
Yeah, we can. So if in doubt, it's always a good idea to go ahead and turn things into cosines and sines, right? So we can use those ratios identities and the reciprocal identity for cosecant to get these in terms of sine and cosine. All right. And then it looks like I've got it, right? So cosine times 1 over sine, that's cosine over sine, and plus sine of x there by the ratio identity is equal to the right-hand side. So when you're doing these, essentially, hopefully the hope, okay, so my hope in making these projects up is that they'll get you to think of a nice order to put these in, but they'll also sort of have you work on one side to get to the other and sort of think of the things that I use in terms of identity. So we said to go from here to here, we use the reciprocal. So just sort of be thinking about these things as you go through, and ratio identities. And algebraic steps you don't really need to document. Here we use another ratio identity. The ratio of cosine and sine is cotangent. And those would be some steps to prove it. So once you have them in order, you leave them like that and go on to the next one. And then finally, the last one is sort of one, is it true or false? So there might be a mistake in that last one, or it might be perfect. We want you to sort of see if it is right, explain why. If it's not, you want to fix it. Okay. So that's going to be sort of the idea behind that project. Gives you some more practice there. Okay. Back to my notes. Come on. I think that's it. Okay, yeah. Hopefully I'm back to my notes. Yes, yes, yes. Okay, thanks. Let's look at another example here. So I have cosecant of b minus sine of b is equal to cotangent times cosine. Okay, so, in this case, it doesn't look like there's any more complicated side either way. But one good technique is to sort of, think about things in terms of sines and cosines, right? So that can be a good technique for us to use. So Jonathan, if I'm looking at that left-hand side, I'm just going to do some scribbling down here. If I'm looking at that left-hand side, what would that left-hand side look like in terms of sines and cosines?
One moment.
Mm-hmm. And then
It'd be
let's
1
see.
over sine minus sine.
1 over sine b minus sine b. Excellent. Great. And then what about the right-hand side there, Caleb? What would that be in terms of cosines and sines?
Say again.
What would the right-hand one be in terms of cosines and sines?
1 over cotangent and minus cosine b, right?
Okay, so
Oh,
cotangent.
1 over tangent.
Okay. So that would be another way to express that first one, but that's not in terms of sines and cosines, right? So what's cotangent in terms of cosines and sines? Do you remember?
No, sorry, I don't.
Okay, no worries. What do you think, Emily?
It would be cosine b over sine b times cosine b.
Okay, yep,
Right.
that's it.
Okay.
Very good. So that's that ratio identity there. Okay, sweet. So now if I look at those, I notice over here I have 2 terms, and over here I have 1 product there. So what I might want to do is start with that left one and put it together. So sometimes it's helpful to do some scratch work on the side just to see where we're coming from and going to. So that's what I'm going to try. I'm going to try to start with the left-hand side here. And I'm going to start with cosecant b minus sine b is equal to 1 over sine b minus sine b. So if I want to put those together, what is my least common denominator there?
Sine of b.
Yeah, sine. Yep, sine b. So this is like a sine b over 1, right? So if I get these both over sine b, the first one's there, right? It's 1. The second one, I have to multiply by sine b in the numerator and sine b in the denominator, right? So I'm going to have sine squared b all over
Sine b.
sine b. Yeah. Don't worry, I haven't forgot about the square yet. I'm just going to have to change my pen now. Okay. All right. There we go. All right. So now let's again look over to the right-hand side that's simplified. Notice here I would have a cosine squared b over sine b. So is there any way to get that from what we have over on the left-hand side? Go ahead, Benjamin.
I'd suppose I got the identity. It's cosine to the power 2 because that 1 minus sine to the power 2.
Awesome. So the 1 minus sine squared is cosine squared by the Pythagorean identity. Nice. And then finally, we can split that into cosine b over sine b. So now I'm just looking at what we did over there to the right to sort of fill in the details times cosine b. But we know that cosine b over sine b is cotangent b. That's that ratio identity. Hey, and that's the right-hand side. Okay. The ratio identity. All right, so here we got common denominators. We use some of those identities to develop the right-hand side, but notice that there we also use the technique of turning things into cosines and sines to get through. Questions there? All righty, let's go ahead and look at another one. So it's going to be important to get some good practice on these. And I know that the software is not good. Like this is sort of the disadvantage of not being able to turn things in. So when you're working in the software, it's going to be important to write things down and try to prove this because there will be a proof on your next exam. Okay, so here, the left-hand side does look a little more complicated. The right-hand side looks pretty compact. We have two terms on the left and we want to turn that into one term on the right. So if we have two fractions we add together and want to turn them into one, do you have a strategy to do that, Ryan? Where we have two fractions, we want to turn them into one? So we can even think of it like this, like if I wanted to add 1/2 and 3/4, how would I put those together? Ryan?
To put them together?
How would you do it? So it's sometimes easier to sort of think about like things in an easier context, like adding fractions. When we add fractions, we have 1 part shaded over 2 parts in a whole plus 3 parts shaded over 4 parts in a whole. So we can't just add those up how they are. What do we have to do first? Okay. Can you help them, Gavin?
Multiply the 1/2 by 2 over 2.
Yeah, great. So we need to find the equal parts in a whole. Great. So we would have to, for this one, we'd multiply by 2 over 2. We would get 2 parts where the whole is divided into 4 parts plus 3 parts where the whole is divided into 4 parts. So that's 5 parts out of the whole. So we can do the same thing for more complicated expressions. So if I start with that more complicated side, what is the least common denominator of a 1 plus cosine and a 1 minus cosine? Go ahead and blurt it out if you know it. So those denominators are both different, right? So if I had like a 1/2, well, it's sort of like the one I just did, right? If I had a 1/2 and let's say 5, or let's not use halves. Let's use like a 1/3 and a 1/4. tenth. There we go. If I had a 1/3 and a 1/10, I would need a 3 from this one and a 10 from the other one, right? So when I have two things that don't have anything in common, then I just use them both, right? So my least common denominator here is going to be 1 plus cosine times 1 minus cosine. So I'm going to build those fractions up to be over that least common denominator. All right, so to do that, I'm going to have to take that first fraction times 1 minus cosine to build it over the common denominator. I'm going to take that second fraction times 1 plus cosine, because that's what it's missing. And now, if I put those things together, I have, so the first one, I multiplied both numerator and denominator by 1 minus cosine. And the second one, I multiplied both numerator and denominator by what it was missing, which is 1 plus cosine. Okay, so now I can add the shaded parts together, which are the brown parts. So I have 1 minus cosine times 1 plus cosine. The cosines sort of subtract out, right? So I get 1 plus 1 is 2. Hey, that looks good. And then in the denominator, I just put those over the parts in a whole, which is just this product, the least common denominator. And one of those should be minus. This is a minus there. Let me fix that. 1 minus cosine. Okay, so now I've taken two terms from the left and put them into one, which was desirable. Okay, so now the last thing I need to do is get a cosecant squared there. So let's go with Michaela. If I want to get that cosecant squared, I sort of need to figure out how to simplify that denominator. So if I multiply the denominators out, what would I end up with? That's like a difference of squares, right?
Would it be 1 minus cosine squared x?
Exactly. Nice job, Michaela. I know I could count on you. Good job. So it's going to be the first one squared minus the second one squared. Okay, so all we've done so far is algebra. We haven't done any trig, but now I think it's time to do some trig, right? So Caleb, what can we replace that denominator by?
Doesn't that equal sine?
Yeah, great. Nice job, Caleb. So that's sine squared by the Pythagorean identity. So I'm going to put that here by Pythagorean identity. And now the last step I might see is, 1 over sine squared is going to be cosecant squared. So I have that's equal to the right-hand side. Great. That's right-hand side by a reciprocal identity. All right. Awesome. So we did use two sort of trig identities there to get to the right-hand side, but we used another technique. We took two fractions, we put them together into one because we knew we wanted to get that right-hand side to be one fraction there. Questions there? All right, okay, great. So let me see, I'm wondering sort of what I want to do next. I'm keeping cautious of time, but let's just go ahead here. So here's some really quick problems. All right, so go ahead and take a look at this first one, number 99. So improving that identity, which is a valid step. So I want you to take 1 minute, and I want you to show what's a valid step to be used to prove that identity. So think about that, and I'll get back to you in 1 minute. There you go, sweetie. You're fine. All right. right. Almost ready to send it. So we're going to go into chat and we're going to put it, but don't send it yet. So put the letter in chat for 99. So which is a valid step to prove this identity? Okay. So in 3, 2, 1, send it. All right. I have two responses. 4. I love to see that ticker go up. 7, 8, 9. 3 more? No, 2 more because I'm in here. 2 more. 2 more. 10. 1 more. 11. Okay, thank you. Thank you. Okay, so B, A, B, A. Oh, there's controversy. Okay, so there's a few more A's than B's. Let's take a look. So when I'm looking at this, if I have, well, let's just look at some that it wouldn't be. So one thing we would never do is take an identity and square it. So this is never right. We can't just square identities because that changes the whole thing. So we can eliminate that part D first really quickly there. I'm having some issues here with Zoom. When you notice, okay. The next one, okay, so yeah, the next one is a no-no. So thanks for not falling for C and D. When we have 2 denominators here, we can never split one numerator over 2 denominators. We can do the other way, but we can't do that. So these are definitely no. All right, let's look at B. So B looks like what they're doing is they're multiplying by this conjugate, right? And they're multiplying by the conjugate in the numerator and denominator. And that might help because it's a valid step. And that would sort of turn this one term or 2 terms maybe into 1 term. So you can sort of maybe think about that Pythagorean identity working for part B. And A is not totally correct because this would be this cosine squared would be 1 minus sine squared by the Pythagorean identity. Well, you know what? It actually would be valid. I have no reason to believe it would not be valid. So it seems like that could work too. So I think either A or B is going to be valid there to work. I think probably the first step you would do is B and then go on to A. So I think you're all right. Way to go. Yes. All right.
No.
Oh, yeah, go ahead. Sorry. Go ahead.
Sir?
Yeah.
We can do A because we have cosine square. And on the equation, it's only cosine. So we cannot do A, I think.
Right. So that's a good point. So we might not want to do A because we probably wouldn't want to multiply by cosine and cosine on the left-hand side. So probably B would be more desirable in getting our identity done. If we went through and multiplied by cosine in the numerator and denominator, we could have a setup like A. And what would happen? What would happen if we did that? I'm trying to think. So then we could cancel out the 1 plus sign and we would have
same problem.
Actually. So I really think that probably B is desirable, but A would possibly work too. Okay. The last one I just wanted to show you is, sometimes identities don't totally work or you have to make sure that it's really an identity. So there might be a value of X that you can plug in here that would make this identity, the supposable identity, not true all the time. So one way we can do this, we can think about this is by graphing it. And I don't think I want to graph this one here, but I think I want to skip that for now. But there is one value here that makes this not